Vectors. You may have heard of these in a physics class or a previous math class. But what is a vector? A vector has magnitude, or in other words, distance, or some even people call this length. So it's measurable how big it is. A vector has magnitude and direction. This direction is what makes a vector truly a vector, meaning it is different than a scalar. A scalar has only magnitude. So what are some examples of vectors versus a scalar? Think about some real life things. So what just has something that you measure but direction doesn't matter? Well, time. Time clicks by in seconds and hours. There's not a direction. Another thing would be temperature. It's 80 degrees outside. Now temperature can move up and down, but if you just measure temperature, it just has a number associated with it. Also mass. Mass is how big something is in grams. Another word might be volume, how big something is. So now that we've talked about scalars, then what could be a vector? Well, a vector, probably the biggest thing, would be velocity. Now that's different than speed, although in the everyday world people use those interchangeably. Speed is a scalar, it just tells you how fast you're going. Velocity is how fast and in what direction. For example, I'm going 30 miles an hour east on 1960. That would be a velocity. Gravity is a vector. Gravity is acceleration due to gravity, and it's pointed toward the center of the earth. Because of gravity, we have weight. Right? Weight is different than mass, because our mass is the same whether we're on the moon or the earth, but our weight changes due to gravity. Think about some other possible vectors and scalars, and you should be able to come up with just a few more. But the key difference is that vectors have direction, where scalars do not. We can represent a vector by an arrow. So I've seen one here. The point P here is called the initial point, or believe it or not, the tail. And Q is called the terminal point. Where do we end up? Or the head of the vector. In a lot of physics classes you'll hear head and tail as opposed to initial and terminal. One way to write a vector is what's called component form. See this notation? We have a V for vector and a little arrow above it. Some textbooks just use a bold marking because that arrow is kind of difficult to print. Again, you can't do a bold, so sometimes an arrow is good. Component form, these little, arrows, I guess, where A is the X component and B is the Y component. So let's look at the vector PQ, and we want to write PQ in component form and then graph it. So we need to know this formula. Terminal minus the initial. Order is important because if you do it the other way around, you're going to get a vector pointing that direction, and again, direction is important. So it says vector V is x2 minus x1, or in other words, terminal minus the initial. So I'm going to have 4 minus 1, and then I'm going to have 6 minus 2. And so this vector can be written in component form as 3, 4. Now how can we graph that? Well, we can graph it by starting with the initial point 0, 0. So I'm going to go right 3 because that's in the x direction, and up 1, 2, 3, 4 in the y direction, and that's my vector PQ. Some books call this a position vector, it is very convenient because our initial point is 0, 0. We end up with 3, 4. Now if this was to the same scale, I want you to look that this vector and this vector, again, if it was the same scale, they would be parallel. You're just shifting it over. But the components are the same in that I went right 3 and up 4. So it's all about that x, y form. Well, how can you add vectors? Well, you can add vectors graphically and algebraically. We are going to do both. How are we going to find u plus v? Well, we can go through and let's just write these in component form. So here's u, here's the initial, here's the terminal. You want to, how do you go from point A to point B? Well, you want to go x first, so I'm going to go 1, 2, 3, that's to the left, so that's negative. And then I went down 2, so that's negative also. Let's look at vector v. Here's the initial, terminal. So how do you get there? You want to go in the x direction first. 1, 2. That was to the right, so that's positive. And I'm going to go up 1, 2, 3, 4, 5. All right, now let's look at vector w. Again, we start with the initial, end up at the terminal, do x first. So I'm going to go left 2 and up 1. So those are the components forms. Now to actually add them, you just want to add the components of it. So u plus v. Let's just make sure I'm grabbing the right parts. So I want to add those components. That would be -1. Add those components, and that would be +3. So let's look at it graphically. What would the graph look like of u plus v? Well, let's regraph u, and again we can pick anywhere as our initial pointing as long as we go, let's see, what does it say to do? Left 3, down 2. 1, 2, 3, down 2. So there's u. Now I want to do v. Alright, so from the head or the terminal point of u, I want to go right 2 and up 1, 2, 3, 4, 5. And that would be v. Now hopefully you can see how these are definitely parallel. They're just moved to a different starting point on my grid paper. So that tells me from the beginning of u to the end of v. This is u plus v. This is called adding head to tail, head to tail. Alright, so let's see what u plus v is. From the initial point, I want to go left 1 and up 1, 2, 3. Well, sure enough, left 1 and up 3. That's the graph of u plus v and the component form of u plus v. Let's see if we can do number 2. We want to do w plus v. Alright, so we want to add those two together. Well, if I add the x part, I'm going to get 0, and if I add the y part, I get 6. Well, let's see if that works graphically as well. I sure hope so. So if I have w, I'm just going to erase this. Right, so there's w. Now I want to do v. Well, v again is to the left 2 and up 1, 2, 3, 4, 5. There's v. So this part is w plus v. Right? Does that match my answer? From here to here, I went side to side none and up 6. So that matches my graph. Alright, the third one, u minus. Now what is minus? Minus is opposite. So I want the opposite direction of w. So this would be, instead of going left 2, I would go right 2. Instead of going up 1, I would go down 1. So this vector would be minus w, and I want to add u to it. So I'm going to come over here with some more space. So let's see, start with u. U is 3 to the left and down 2. That's u. And now I want to do minus w. Well, minus w is 2 to the right, and again I start at the terminal point here, 2 to the right and 1 down. That's minus w. So from the beginning to the end, u minus w. Let's see, this would mean 1 to the left and 3 down. So U minus W should be -1, -3. Well, let's check that out with the numbers. If U is -3, -2, W is -2, 1, and I want to subtract, I would have -3 minus a -2. Look at what that equals. Okay, those are the x components. And then I would have the y components of -2 minus 1, which is -3. So hopefully you are seeing that it all matches up. I would like for you to go ahead and finish number 4. But number 5, how do we do that one? Well, we can multiply by 2. Well, that just means to double the length of the vector. So again, with some computer magic, I can erase some of this so you can kind of see what is 2W. Well, I just need to do it. I went over 2 and up 1. I'm going to go over 2 and up 1. And so there's 2 of those. So this would be 2W. So what are you doing? You're just multiplying the components by 2. So just 2W would be -4, +2. Again, multiplying the components by 2, and then you're going to add V. So let's V was 2, 5. And if I want to add those, just add the components. And I would challenge you to do that. Let's see, I have it right here on the graph. How convenient is that? So from the beginning, 2W plus V, that would be, this vector is 2W plus V. And hopefully you can see that from here I went left 2 and up 7, and that is how you add graphically and components. Remember, it's head to tail, and then you have the result or your answer.